When we get to the flexible mode and turn it on, we're going to see what it looks like compared to what's in the custom DOE platform. Has a lot of the same features, but not everything that is fully supported here. And so one of the things is you'll see that if you look on the right here, this response tab is gone. The defined factor constraint is gone. The design explorer is gone. And there's one not shown here, but there's a covariate candidate run set that would have been hidden under this factors option if it was open. But the main part, this design generation part, is identical. So this is where we get to tell the flexible mode, the easy DOE flexible mode, hey, I do want some blocking. I do want some center points. I do want some replicates. I would like to adjust the number of unique trials or the number of user specified trials. So this part is the important part that is the same. So, and the flexible mode is on the analysis side is a shortcut to the generalized regression platform. The safest thing to say right here is that the default settings are robust, meaning it's highly likely that's what you're going to want to do with your analysis. Again, this is meant to be the easy mode, and it's unrealistic to explain all the features and options and statistics behind the choices in the generalized regression platform. So I have no intention of covering that today, but the developer, the primary developer of that platform is Clay Barker. And there are 3 recorded tutorials of his on using the generalized regression platform. And in particular, the first of these 3, he's mainly focused on how do you analyze designed experiments with the GenReg platform. There's another one for observational data. So think that's haphazardly collected data. Somebody's brought you a pile of data and said, hey, can you analyze this? That's a lot different than they're bringing you a designed experiment. So I would encourage you to check out these developer tutorials if you want to learn more about the generalized regression platform. So why do we want to use the flexible mode? We want to use it when we want more control over the design. In particular, when we want to specify the number of blocks, the number of center points, the number of replicates, the total number of runs, and to tell JMP that one or more of the factors are hard to change. And we'll talk a little more about hard to change in a little bit. The other sort of group of reasons why you would want to use flexible mode are on the analysis side. So when it comes to fitting a model, you might want to change the estimation method from the default best subset. Generally, I would say probably not. You might want to change the estimation method under the advanced controls. This would be where maybe you would want to force in the heredity or force in certain terms in the model, and we'll illustrate these. You might want to change the distribution type from the default of normal, and in this case, we'll illustrate applying a log normal distribution. You might want to change the validation method from the default AICC, which stands for Aka-Iki Information Criteria, and the little c stands for corrected, and it's been corrected for small data sets. And that's generally what a designed experiment is, a small data set. So more than likely, you want to leave that alone. But if you have a reason to want to change them, this is where you would have that option. So applying these specifically to the paper airplane problem, here's the things we might want to control. So on the design side, the number of blocks. Think about this. We ran the analysis and nothing was significant. So you're thinking, I need more data. Let's do it all again tomorrow. But did the wind shift? Was there a learning curve to making these paper airplanes? Are people's arms sore today from having done all that airplane throwing yesterday? Was yesterday hot and dry and today's cool and damp? So what we're getting at here is there can be an unknown factor that's correlated with the 2 different groups of tests that you're doing. And they can be in combination. So what you're really interested in with blocking is the data I collected yesterday and the data I collect today, are they statistically significantly different from each other? And if the answer is yes, that doesn't bode well for predicting tomorrow. Okay, you're hoping there's no difference with a blocking factor. Now, what it also means is if it is significant, you've got some detective work to figure out why the results are so different from day to day. So it's a cheap Solution, it only costs you one more run typically in a design to add a block. And so we highly recommend it when you have this situation of restricted randomization between I did all this stuff yesterday, I'm doing all this stuff today, and we don't want to, what we want to know is, did the process shift between those two groups? Changing the number of center points, we're not going to do a lot of that today, mainly because the data that Peter has, there's only one continuous factor. So there aren't a lot of center points to be worried about here. But the number of replicates, this is the real problem we detected. There were barely any significant effects in his paper airplane model analysis. So what we want to do here is, because of that poor signal to noise ratio, we want to increase our chance of detecting effects by shrinking confidence intervals. And the way to do that is take more data. So ultimately, we want more numbers of runs and increasing the number of unique settings. We're going to find that in his experiment, if you actually looked at it, because he only ran 18, there were 24 possible combinations of the 2x2x2x3 sort of design space. And it turned out the one that is the optimum was actually not chosen. So, that's the kind of thing where we could increase the number of runs to ensure that that does get chosen. And finally, we'll illustrate an example of what if a factor is hard to change. On the fitting model side, these are the kinds of things we'd want to change, but once again, by the default of best subset for estimation method, I would stick with. Under the advanced controls, this is where, again, we might want to force in all the main effects and also potentially enforce heredity. We will show how we would want to change the distribution from normal to log normal in this case. Probably not likely to want to change it, but you could from the information, aka information criteria there. And at this point, we're not really going to compare fits of different models. So we'll call this Peter's process, and we're going to make a modification to it. So we're going to call it airplane 1.1 in flexible mode. Same response, same factors, but what we want is, and we still want a response surface model, so top three bullets are the same. Where it starts to get different is point 4, is we want a total of 36 trials to shrink the size of the effects detected. And this is where I point out, if you only have 5.5, 8.25, and 11 as the range, as the levels of the continuous factor, there's only really 24 combinations possible. And we're going to want 36, which means at least 12 of ours are probably going to be repeats or replicates of the other 24. Here, if we believe the data are not normal, we might want to use a log normal distribution. Now, why would we think it's not normal? Most people realize that when you have data that changes over a wide range, we often end up putting things on a log scale. And so here, think about it. If you had a full combination of settings where the plane only goes 10 inches, and you got another combination of settings where it goes 100 inches, you got another combination of settings where it goes 1,000 inches, let's just say that you treat that as normal, and you come up with a standard deviation of 50. Well, when you throw it 10 inches, do you really expect the variation to be plus or minus 50 inches? It's probably more, I'm just going to pick a number, probably more like plus or minus 2 inches. And so as you keep going up in size, you can see the variance or the spread in the data is increasing. Well, if you do that on a log normal distribution, you pretty much linearize that variance. So that's why we might want to use a distribution other than normal. And then, as we said, we might want to force all main effects into the model. So we're going to go do this. And what I'm going to do is bring up the factors for this problem so that you don't have to watch me type them all in again. And there's the design generation platform where it's currently set at 18. Okay, and what we're going to do is we're going to generate a 36 trial design for this. So let's go use the flexible mode platform to do this. Looks like we're going to open up that file again and save the factors for use in a new DOE, and then we'll also reanalyze with the GenReg platform. So let me go back out to JMP. I actually have it already done. This is what we're going to create. I want a file that's got the information for the factors. But the way I would do that would be if I had that original file open. So this is the original file where those factors have been defined down here. I have an option to save the factors. And so you'll notice that file looks exactly like this one here. Okay, and so this one on the right, I've already saved it with that name. But that's how you can get the factors out. If someone has a file that is already a design, you don't have to type it all in again. Okay, and now while I've got this open, let's move along on the flexible mode to that analyze stage, where here, now if we choose to do the modeling, we've got some other options. And so this is by default what has already been done. But if I wanted to do a new one, I would click this model launch. And here's where maybe I want to change that distribution from normal to log normal. And then here, I want to stay with best subset. I can't think of a good reason to change it from that. Here under advanced controls, this is where I can say enforce that effect heredity. And here's where I can say, let's force the main effects for all of these factors into the analysis. And so if I do that, and again, here's the validation method, I don't have a good reason to change it to one of these other ones, so we'll stick with AICC, and we'll click go. And what I'll get is an answer, which at the top, under model comparison, it's going to have, what was sort of there with the normal best subset, and here's what you would get with the log normal best subset. And let me do one more version. So if I go back to here, I'm going to change this back to normal. I think that's the only difference I want to make. So if we're still under the normal assumption and we click go, you'll notice we'll get a third example up here. And you can still see that the trade-off here is this top one has the lowest AIC. So by that information criteria, that's suggesting that this is the best model. But if I compare the R squares here, you can see that the R square for the normal with 7 terms in it has a higher R square. So, this is where we're trading off complexity versus, what might be indicated to be the best model. So all 3 of those models are here, okay? And this is where you can do a lot more investigation of the model in each of these cases. And you should be able to, if you want to look at any of these, we can turn on the profiler. And what I want to show you is if I hold the control key and say turn on the profiler, it should do it in all 3 of these outputs. So there's the original model. There it is with the log normal. And there it is with the normal, but I've got the extra terms in it for interactions. So a lot more analysis capability there on the GenReg platform. Then that's in the flexible mode in the DOE, easy DOE. Where we want to go next is to load the factors for the new DOEs and generate several different designs where we use block size, center points, replicates, and user specified. And then we'll do it again, but we'll add in the hard to change factor. So let's do the first one. So if I go to my factors, I'll open those back up. So if this is the currently open data table, okay, and I go into DOE and I pick easy DOE, or really if I pick any DOE platform, if I go to the menu item that says load factors, it's looking for the currently open data table. So when I do that, it's automatically brought everything in where we had left it. Now I still have to have a response, and I did not save the response, but if I had done that, there was an option for load response. So I'll just type it in again. That was distance. And I think we had units of inches, and there's no specs or anything on this. But if I've got this all set, now we're more or less repeating the guided mode here a little bit. But if I make the next step is the model, we pick this case, the next step is the design, we pick that case. Now we've got the 18 that we had from what Peter actually did. Okay, and this is where now we go out, we analyze, and we find out, oh my gosh, nothing's important. What if we knew that already? And now we're going to go at it again, and we decide we want to do 36 experiments. And so let me see if I can go back here, and I could change this to 36. And so when I do this, I'll get a bigger design. And one of the things I want you to see okay, it's certainly bigger. If I export it, one of the really clever features on the rows menu, you can almost see everything here, is if I take these 4 columns and I try to eyeball where are things duplicated, it's kind of hard. But there is a row selection option that says, you know what, select the duplicates for me. So when I do that, you can see that the first 19 are all unique, and then 3 replicates came in. Then row 23 is another unique. And so the bottom half of this is loaded with our replicates, and there's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is, we know there's only 24 unique combinations, and we asked for 36. So one thing I could do here is if I hide and exclude these, okay, and just to show that if I now made a graph, like a scatter plot matrix for these 4 factors, it should be no surprise. That's all the pairwise combinations of them, but that you can see how balanced everything is in the design here. And if we, that's really the main point. So we're very, very limited in the number of combinations that we can even test. Okay, so now what we could go out, run the analysis now with our 36 trial design. But the one thing we didn't do was take into account, what if we have to do this over 2 days? So if we wanted to do that, what we might want to do is go into the flexible mode. We'll go back to Easy DOE, load the factors again. And again, I guess I got to put my response in. And we'll click flexible mode, and we'll go to model. And now you can see, rather than picking sort of from that list with numbers, I actually have sort of control over what's in the model. Now, by default, these are the 4 main effects, okay? And down below here, it's telling me, yeah, there's a total of 5 terms in the model, the intercept and those 4 main effects. Well, we know we want an RSM model, so we hit that. And now it says, yeah, there's 12, and what you're going to need are 18. But we can't do more than 18 in a day, let's say. So now what I want to do in this flexible mode is actually do some blocking. So right here, I've got the option to group runs into random blocks of size 18. If I could only run 12 in a day, I would put a 12 there. But if I now click this and change this, notice it automatically went from 12 to 13 terms in the model, because there's 1 more term for the block, and it automatically went to 18, jumps to default designs are 6 trials larger than the terms in the model. But if I make this a 36 now, it's going to give me 2 blocks of 18. So we'll go and make our design. And you can see that the first 18 are block 1, and the last 18 are block 2. And once again, we could go in here and look for duplicates and things of that nature. But now we know we've got a design that's going to have enough data to have some significant effects. All right, that was redoing the process with the flexible DOE platform for what I called Airplane 1.1. Now we're going to go back and do it for 2.0, where we're going to change a few things. We're going to have 2 continuous factors. So the width of the plane is now a proportion of the length, and the range is 0.4 to 0.8. Instead of a categorical paper weight, which was cardstock versus, say, letter, we're actually using the weight of the paper in pounds. And so this is a discrete numeric, 20, 24, 28, 32. If you went to your local stationery store, they don't sell a 26, 27 pound paper, but you can buy 24 and 28. And now for throwers, we're going to keep that categorical, but I'm bringing in my father-in-law. So we've got a senior in this group, even though a lot of people would put me in that group. And then we've got the launch site, which in this case is categorical, but it's also hard to change. It's the height of the deck. So we got to walk up a bunch of stairs to throw off of that. And do we want to do that, all 36 times, sort of randomly, or do we want to do a whole bunch at the top of the deck, and then we'll do some down below, and then we'll go back up? So that in our case is the hard to change factor. We still want to support a response surface model. We want that total to be 36. But notice now how big the number of combinations are. It's 3 by 3 by 4 by 3 by 2. So, there's at least 216 possible combinations. We only want 36 of that. So the sort of creation of replicates is unlikely unless we force that to happen. And again, if we think the data are not normal, we could use the log normal distribution, and we can also force in main effects when we do the analysis. So once again, to make life simple, I'll open up a file that's got all the factors and ranges and settings in it. And then we'll see this part of the dialog box where now you'll see that the block size, center points, and replicates have disappeared. That happens because of the hard to change factor. And then what does appear is the number of whole plots. And in this case, we're going to do 6, but we could do as few as 4, maybe. We could do more. And that just means how many times are we going up and down the stairs? And even with whole plots ignored, all combinations of 5 factors are unique. So this is what we're going to be able to make if we decide to have 4 blocks, or 4 plots, 6 plots, or 9 plots. So let me go out and bring back up the jump. And here are the DOE factors. And if I were to go in to one of these factors, in particular launch site, and I go to the properties, you can see that there's a property here called role. Actually, maybe an easier way to do it is to just look at the top level of this. You'll notice here that this is the information about that column. And right here under column properties, under factor changes, is the option for hard. So that's where you could change it here, but that's how it got recorded when we just saved out these factors. But with that being the active file, if I go back to DOE, easy DOE, and I say load factors, it's going to bring them all in, except it didn't bring in launch site. I got this message. One or more of the factors is not compatible with the guided mode. So I need to switch this to flexible up top. Let me bring in the factors. And it adds that one that was not compatible. And right here you can see it says, yeah, this one's hard to change. So I had to be in flexible mode for that information to be brought in. Once again, we're going to be interested in distance. And now we'll click the navigation control, which takes us to the model, where once again, we look down below here. Currently, there's only 7 terms because by default, it's the main effects model. I want to change that to RSM. And now the number of terms has gone up to 23. And by default, the number of whole plots is 4. I want it to be 6. So I actually have 6 sets of 6 trials in my, and here's where I can tell it, 36. So I purposely, upped that number because I want to be able to detect those tiny effects. So you can see we've changed this part in the flexible mode, and it's driven mainly by the fact that this is hard to change. But with that set, we can click the design. Takes a little longer when there's 216 combinations to pick from instead of 24. But it has completed that task. Again, you can often tell by looking at the little histograms at the top. Here are I've sort of colored by whole plot, so you can see which ones. And if I add the rest of the columns to this, you can see across there. So notice it goes deck, yard, yard, deck. Well, when that happens randomly, you might want to actually swap these two, because guess what? I may have saved my father-in-law walking up and down the stairs one time. And what you really want is, this should be a fresh start each time. So this will work, the way it's set up, but the whole idea of the whole plots and blocks is to, capture that variability. All right. And this one actually turned out that I've only got 3 levels for length and width, which when I've done this other times, let me just go back to the slides on this. And I wasn't as lucky. And so when I made this design, if I zoom in here, you'll notice sometimes it snuck in that like 9.625. So in other words, it wasn't just 5.5, 8 1/4, and 11. It gave me some others in between. And this can happen with the optimal design tool. So if you wanted to force that to not happen, you can actually remake length and width into discrete numeric factors. And when that's the case, then you don't allow JMP to pick the intermediate value between your midpoint and your high point. So that's just a trick you can use if you would find it inconvenient to have certain intermediate levels of your continuous factors. Okay, I probably should have paused a while ago for questions, and so because we're almost done. But before I wrap things up, Olivia, do we have any questions that we should be addressing for the crowd?
One that just in that last example, and I was typing the answer, but you can probably answer it faster by talking. But there was a little confusion between blocks and plots when you did that last one. They're not familiar with plots term. And what is block?
Yeah, whole plot is associated with the way that the models are going to be analyzed. When we block, it's usually we're blocking across. I got 3 bags of raw material, and I think they're all the same, but one's got maybe an older date code. And it's more like a check to see, is that bag, so much out of date that it's shifted the process, or the shift from day to day. We don't really think there should be an effect, but it might show up. Whole plot is more about the variability within that setting is larger than, say, the between factor settings. So there's like factors within a plot and factors out. And this really came out of the agricultural analyses that was associated with DOE in the beginning, where you had these hard to change things like, the irrigation for a field or the amount of, fertilizer in a field. So blocks and plots seem similar, but the analysis of the whole plot is a little more rigorous with the REML. And again, this all happens automatically, and this gets into a more advanced conversation than we typically have in the easy DOE part. But when it's hard to change, that's the indication that you're going to have whole plots instead of blocks. And I hope that answers it. Yeah. So kind of wrapping up, we use flexible mode when on the design side of things, you want to change the number of blocks, you want to change the number of center points, you want to change the number of replicates, or even the total number of runs, and when you have a factor that is hard to change. It can be more than one hard to change factor. And on the analysis side, it's when you want to change the estimation method. But again, this is the part where I feel like the defaults are pretty robust. You want to change your estimation method. You want to change the distribution from, say, normal to one of the other ones. And you might want to change the validation method from the default. And I would say normally you wouldn't want to do that either. So really flexible mode is probably more about the design, but there are some options available to you to improve your analysis.